My name is Jain Reddy from ECB section. Welcome to another session in this 15 days student development program. Today, our special informative talk will be handled by Mr. Satyam Garu, Assistant Professor, Department of ECE, Mohan Babu University. Welcome, sir. Welcome to the session. I'm
Welcome.
requesting Satyam sir to take over the session. Thank you, sir.
Thank you, Jay. So, hello everybody. So, let me present now then. Is it visible?
Yes, sir.
Okay. So, good evening everybody. So, I'm Satyam and I'm thankful to the organizers who has given me this opportunity to present the area which I like, that is antenna. So, my talk will be on antenna design and fabrication with a special focus on millimeter wave applications. Okay. So actually this is the low profile miniaturized wideband antenna for millimeter wave applications. So this is my present area of research. So I will link my today's talk on this somehow. One or two points I will touch so that I will make a proper resemblance with the main topic, right? So this will be the flow, that is antenna introduction and software tools limitations. Means how many softwares are there for the antenna design, and on what tools, on what integration method they are they are based, right? So that's what, followed by microstrip patch antenna design and fabrication. Here we will see how we can fabricate a microstrip patch antenna using PCB techniques, right? And then we'll see some basic of millimeter wave applications, millimeter waves, right? And then some design of the millimeter wave antenna. The last one being the topic of this, right? So this I will connect at the last. Okay. So yes, so as you can see, there are a variety of antennas all around, right from mobile tower to early days televisions. So this is a Yagi Uda, right? Then satellite communication, and then in radars, right? So in radars, and then in other satellite communications, right? So these are the variety of applications, right from mobile to big reflector antennas, right, like this. So of various frequency and of various sizes, right, for different applications also. So antenna is inevitable. So then I would like to present one. I would like to say some video here, a demo for the antenna. So let me just spend some time on this. So just I hope it is visible.
Antennas are widely used in the field of telecommunications, and we have already seen many applications for them in this video series. Antennas receive an electromagnetic wave and convert it to an electric signal, or receive an electric signal and radiate it as an electromagnetic wave. In this video, we are going to look at the science behind antennas. We have an electric signal, so how do we convert it to an electromagnetic wave? You might have a simple answer in your mind. That is, to use a closed conductor, and with the help of the principle of electromagnetic induction, you will be able to produce a fluctuating magnetic field and an electric field around it. However, this fluctuating field around the source is of no use in transmitting signals. The electromagnetic field here does not propagate. Instead, it just fluctuates around the source. In an antenna, the electromagnetic waves need to be separated from the source, and they should propagate. Before looking at how an antenna is made, let's understand the physics behind the wave separation. Consider one positive and one negative charge placed a distance apart. This arrangement is known as a dipole.
Actually, this is important.
And they obviously produce an electric field as shown. Now, assume that these charges are oscillating as shown. At the midpoint of their path, the velocity will be at the maximum, and at the end undergo continuous acceleration and deceleration due to this velocity variation. The challenge now is to find out how the electric field varies due to this movement. Let's concentrate on only one electric field line.
Just here you pay attention, right?
The wavefront formed at time 0 expands and is deformed as shown after 1/8 of a time period. This is surprising. You might have expected a simple electric field as shown at this location. Why has the electric field stretched and formed a field like this? This is because the accelerating or decelerating charges produce an electric field with some memory effects. The old electric field does not easily adjust to the new condition. We need to spend some time to understand this memory effect of the electric field, or kink generation, of accelerating or decelerating charges. We will discuss this interesting topic in more detail in a separate video. If we continue our analysis in the same manner, we can see that at 1/4 of a time period, the wavefront ends meet at a single point. After this,
now he will present the separation, right? This is how waves are separated.
The separation and propagation of the wavefront happens. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. If you draw electric field intensity variation with the distance, you can see that the wave propagation is sinusoidal in nature. It is interesting to note that the wavelength of the propagation so produced is exactly double that of the length of the dipole. We will come back to this point later. This is exactly what we need in an antenna. In short, we can make an antenna if we can make an arrangement for oscillating the positive and negative charges. In practice, the production of such an oscillating charge is very easy. Take a conducting rod with a bend in its center and apply a voltage.
Again, he will say the same thing. So let me just forward it a bit. So this is something about, again, the same thing he will say, right? Let me just go to the Yagi-Uda, right? Yes.
Colored bar acts as a dipole and receives the signal. A reflector and director are also needed in this kind of antenna to focus the signal on the dipole. This complete structure is known as a Yagi-Uda antenna. The dipole antenna converted the received signal into electrical signals, and these electrical signals were carried by coaxial cable to the television unit. Nowadays, we have moved to dish TV antennas. These consist of two main components, a parabolic-shaped reflector and a low-noise block-down converter. The parabolic dish receives electromagnetic signals from the satellite and focuses them onto the LNBF. The shape of the parabolic is very specifically and accurately designed.
Now he will say what is there inside this LNBF, right?
The LNBF is made up of a feed horn, a waveguide, a PCB, and a probe. In this animation, you can see how the incoming signals are focused onto the probe via the feed. At the probe, voltage is induced as we saw in the simple dipole case. The voltage signal so generated is fed to a PCB for signal processing, such as filtration.
Actually, we know when there's a free space, the wave is following T or TM, right, mode. And here, wave is having a TEM mode, right? So there's a change in the mode in which wave propagates. Outside in the free space, it is T or TM. Inside this waveguide or transmission line, it is TEM, right? So that's all.
Conversion from high to low frequency and amplification. After signal processing, these electrical signals are carried down to the television unit through a coaxial cable. If you open up an LNB, you will most probably find two probes instead of one. The second probe being.
This is the probe 1, this is the probe 2. Both are perpendicular, right? To get the two opposite waves, right?
Being perpendicular to the first one. The two probe arrangement means the available spectrum can be used twice by sending the waves with either horizontal or vertical polarization. One probe detects the horizontally polarized signal and the other the vertically polarized signal. The cell phone in your hand uses a completely.
Now we'll see something about the patch antenna where it is placed inside the mobile, right? Just 10 seconds only.
Different type of antenna called a patch antenna. A patch antenna consists of a metallic patch or strip placed on a ground plane with a piece of dielectric material in between. Here, the metallic patch acts as a radiating element. The length of the metal patch should be half of the wavelength for proper transmission and reception. Please note that the description of the patch antenna we explained here.
So with this, it is completed. So yes, so this is something about the working and the functioning of antenna, right? So let's move on to the other slide. So here is the variety, the family of antennas, where we are having end fires. Basically, it is helix, Yagi-Udas, and log periodic antennas, conical spiral antennas. Means here across the end we are having the radiation. Then we are having a loop antenna, right? Dipoles, folded dipole and dipole array. Whenever we make array of any antenna, we know from our basics that the gain of overall gain increases, right? Then we are having stubs, slot antenna, patch antenna, and then we can connect a lot of patches together, making an array. Patch, right? Patch array antenna. Then we are having aperture antennas like horn antenna, reflector antenna, parabolic, lens antenna, radomes, and frequency selective surface antenna, right? FSS, and then corner antenna. Then this reflector can be parabolic, can be corner, can be flat. Each of having their own applications and the limitations, right? So these are the family of antennas, types, classifications. Now, what are the roles? As you can see, as you have seen the video, so we can list out the whole antenna role into four basic subtopics, right? Spatial filter, polarization filter, impedance transformer, and propagation mode adapter. The first one being the role of spatial filter means it is directionally dependent. Means my antenna will be, or any antenna will be very sensitive to one particular direction. That is why practical antennas are directional antennas, right? And yes, second point is polarization filter. Means it will be more oriented towards one particular type of polarization. As you know, there are many polarizations: linear, circular, elliptical, right? Horizontal, vertical. So circular. So a lot of varieties are there. So it is properly oriented, means connected, means for one particular polarization it is having high gain, right? Then impedance transformer means there is an antenna. On one side we are having transmission line, on the other side we are having free space, and both the sides impedance are different. So my antenna should be able to pass more information, means more power, once impedance is matched, right? So that is one thing. The last thing is that is a propagation mode. Means as you are aware, means on the left side of the antenna or one side of the antenna we are having the transmission line, which is the guided structure, or the waveguide, which is a guided structure, where the mode is TEM, right? And on the other side of antenna it is free space, open air, where the mode is TE or TM, right? So there is a change in the mode. So once the antenna is behaving like a transmitter, like a source antenna, so the mode changing from TEM to TE. Once the antenna is behaving like a receiver, the mode is changing from TE to TEM. So there is a adaptation in the propagation mode, right? So that is also one of the roles functions of the antenna. So these are the four broadly defined functions of any antenna, for that matter. So again, it is the same thing. Some directional antenna or directive antenna is there, means which is having more direction, more gain towards one particular direction, right, and less gain or no gain in all the other directions. So yes, so this is what this particular angle is showing the direction of maximum gain, right? So this is the antenna, right? So this is the antenna. So this can be moved, right? So wherever it will move, wherever it will point along that direction or in that direction, gain will be maximum. So that is what this function is. And then polarization. So here it is dipole antenna has been taken. You see, dipole antenna of height h, right? And here you see these are two cases. On this side, it is having the electric field is oriented along z direction, right? Okay. And then what is the terminal voltage V here? V is equal to h dot e. H is the this height vector, right? So this is equal to, this is antenna is oriented along z axis, so height is equal to h into z cap. Okay. E is electric field, incoming electric field. So here it is E naught into z cap. So when you make a dot product, that is h z cap dot E naught z cap into z cap will become 1. That is why the value is h into E naught. Okay, this is possible when h is also along z cap and incident field is also along z cap. So this is the z direction. This is the z direction, right? And then here in the second case, E is along y direction, right? And z is still, and h is still along z direction only. That is why you see this cross. This cross is, it is along y direction. You see this cross here also, y direction, right? So here there is a directional mismatch. It is along y and height is along z. Z cap dot y cap is 0. That is why terminal voltage is 0. Whatever wave is coming here, my voltage, at this point is 0 only. I'm not getting anything. Why? Because electric field here is oriented along y direction, and here, right, and here it is along z direction. So when orientation of electric field along the same direction as that of the dipole antenna, means in that case only we will get the radiation, right, terminal voltage. So that is what the polarization mean. Polarization is the orientation of electric field, spatial orientation of electric field, right, at a particular time. So that is the polarization filter. And then the impedance transformer, as you are aware, the transmission lines are having impedance 50 ohm or 75 ohm, and the free space is having impedance 120 pi or 377 pi. I mean 377 ohm. So there is a lot of mismatch, 50 and 377. So antenna has to take care of all this, right? That is a third issue. And we know from the maximum power transfer theorem that whenever the load resistance or impedance becomes equal to the source impedance, then maximum power from the source can be given to the load. And when there is a maximum power is transferred, and then we can achieve maximum gain for any antenna for that matter. Okay. So here is the propagation mode adapter. As I have told you, here is a generator, here is the receiver. Both are very distant apart, lot of distance in between. Here is the transmission line, here also is the transmission line. Inside the transmission line, the mode is TEM, right? Here is the free space. Here the wave propagates like a plane wave, and here the mode is T or TM. So again on, as I said, on the one side, and this tapered thing is called antenna, right? Horn antenna, let's say. So here it is one mode, here it is another mode, here it is one mode, here is another mode. So like that, it should be able to adapt itself for the proper mode adjustment, right? So here are the software tools, and you see on what is their foundation, on what basis they depend. So first is the total 4 5, we will see 5 I think. HFSS means that is the most important one, high frequency structure simulator. It is dependent on it depends on finite element method, which is very accurate, you can say. And it simulates high frequency EM fields and structure. It dates back to 1980s. Okay. It is also called ANSYS HFSS, right? And then we are having CST, Microwave CST Studio. We can say Microwave Studio. It is started from 1990s. Okay. And then we are having FICO. It is very recent, 1997 only. And it adopts the technique called method of moments. All this technique comes under computational electromagnetics. Under the heading of computational electromagnetics, this finite element method of moment, FTTD, lot of variations are there. Fourth software is MATLAB, which we all are aware. It uses some toolboxes for antenna design, and that toolboxes uses MOM, method of moments, right? The fifth one is ADE. Actually, it is almost MATLAB based only. So it is a graphical user based interface based antenna design tool released in 2017. So I can say out of 5, it is the most recent one, and it behaves like a companion between the MATLAB and the CST platforms. Okay, so it takes it does not replace the CST as you can see from the last line, but it helps as an enhancer, facilitator, right? So in shorter time, it will give you better result as compared to CST, right? So if I compare CST versus HFSS, we will choose HFSS only because of the method, finite element method, right? Here is the microstrip patch antenna. I mean, you see here, this is the substrate. On the substrate, on one side of the substrate, we are having a patch which is made up of metal. This substrate is made up of dielectric, right? On the bottom of the substrate, we are having a ground plane. So this ground plane is also metallic, let's say copper. This patch is also metallic, let's say copper. This is the feed line. So feed line connects the patch, radiating patch, and the transmission line, right? So this is the structure. And as I said, I am working on this millimeter wave antenna. So we have taken a RT Rogers Duride 6002 substrate because of its low dielectric loss. And we know what is dielectric loss. So this dielectric substrate, it is ideal. If it is ideal, what does it mean? It means there is no current propagation, current conduction, right? So if my dielectric conducts very small amount of current, means my dielectric becomes lossy. Very lossy dielectric means it is conducting current, right? So dielectric behavior means current should not go inside. So that is the final line. And then in order to improve the the performance, there are various ways to improve it: parasitic patch, slots, defected ground structures. So a lot of variations. So defective ground structures, like we make some sort of slot, we change the ground dimension, and then we add some defect here means slots, cuts, right? So that makes my ground defected ground, right? Slots means here I write slots we can use on the patch on the top side, and there means slots means cut here also. So here we can make a cut. So whenever we make a cut means we will add discontinuity, and whenever we are adding discontinuity to the structure, radiation and the gain will enhance, right? And the size will become more compact. I mean, we will get miniaturized antenna, right? And then parasitic patches are like patches. Let's say here you can see a patch, but this patch is connected to feed. If I make another patch here or anywhere on the substrate, on the top side of the substrate, without connecting to the feed, then that patch will become parasitic patch. So let me repeat it. Patch, if connected to the feed, is one thing. Patch, if not connected to the feed, is called parasitic patch, right? And then for simulation we will use HFSS, right? So these are the design calculations. So this is the width of the patch, what should be the formula? This is the length, what should be the formula, right? Thickness is coming, I mean it is from the manufacturer side only. So we don't calculate thickness because it is adjustable, right? So we will just calculate the width and the length of the patch, right? So here is the, let's say, millimeter wave application means millimeter wave goes from 30 gigahertz to 300 gigahertz. So we have designed antenna for 30 gigahertz, that is a margin. Dielectric constant we have taken 2.2, that is equal to, dielectric constant is the property of this dielectric, that is the permittivity, right? If it is very high permittivity, right, means it is very high dielectric constant. Okay, then the height of substrate, that is h is equal to 0.8 millimeter. So this height is 0.8 with permittivity is 2.2. And then you can see here the structure of microstrip patch antenna. And here the formula. The first one, that is the width, epsilon r effective. Here's the delta L. Delta L is the, talks about the fringing length, right? Which is not the actual length, it is the fringing length. And then there is the L effective. So first we'll calculate width, right? F naught will become 30 gigahertz, epsilon r is, that is 2.2, c is the velocity of light, right? So we will calculate width of the patch. This width is the width of the patch, right? And then we'll calculate epsilon r effective. Epsilon r has been given, w we know, so from this we can put, this h is the height of the substrate, okay? So then we'll calculate delta L value. Delta L value, here we need epsilon r effective, w, both. So you calculate one, use in the another. You calculate second one, use in the third one, right? So in that way, we calculate delta L, and then we calculate this L effective. L effective is C upon 2 F naught under root of epsilon r effective. You see W, C upon 2 F naught here also, L effective C upon 2 F naught here also. But denominator is somewhat different, okay? And then once we calculate all the four, at the last we calculate the length of the patch. L is equal to L effective minus of 2 delta L, right? So we start with our calculation with the width of the patch. We end up our calculation with the length of the patch, right? So this is the design flow for any microstrip patch antenna for that matter. You see, so this is the what I have made for the millimeter wave communication. So here with this dimension and the parameters, we have designed this, means the patch width is 5 millimeter, length is 7.5 millimeter. Okay, it's all millimeter wave application. Ground wavelength, ground plane length is this. Now you see the length of the ground. Length of the ground is 2.55. Length of the patch is 7.5. This is 7.5 length of the patch. Now you see ground length is less. That is what we mean by the defected ground structure. Width is 5 mm. Okay, slot length means here we have cut a slot. Okay, the length and the width has been given. So this and this, you see, this is the parasitic patch. This is the parasitic patch. Okay. Now, so this is the performance analysis of antenna. Means all antenna we make we make to increase the gain. In the first case, without any parasitic patch, without any DGS, right, without any slot, the gain is coming out to be 6.85 dB decibels. When we do some modification, three modifications: slot, parasitic patch, and the defected ground structure. This green thing you see, this green thing is the defected ground structure. Actually, ground should be covering total thing, but it is not covering the total thing, right? So that is what the defected ground structure mean. When we put all these three, parasitic, slot, and this DGS, we get a high gain, that is 7.04 dB, right? So this is the gain enhancement. Performance, has been enhanced, right? So here is the two things we'll see for the fabrication. First, how we fabricate the any microstrip patch antenna, and then at last how we will solder it so that probe can be connected, right? So we'll see one by one. I think I have double clicked it, so no issue.
Hello everyone, we are going to show you the procedure to fabricate the PCB and microstrip antenna. For fabrication of PCB, we have to go through the following steps. We will fabricate a 1x2 microstrip antenna array, which is simulated using HFSS software. The operating frequency of the antenna is 2.45 GHz. We can also fabricate PCB designed using Eagle software. Different software tools such as CorelDRAW or AutoCAD can be used to prepare negative of the required design like antenna or circuit layout.
You will talk a little bit slowly, so I will increasing the speed so that we can cover the main thing. Let's say 1125.
The negative is printed on the trace paper.
So let me say what he has done. He is showing the steps what he will do.
So everyone, we are going to show you the procedure. We will fabricate a 1x2.
Then he has designed some antenna. Okay, this is the connector soldering. We'll see how to solder at the last. Again, it is a patch antenna. This is the feed. This is the patch antenna. The green thing is the substrate. Okay. So this is the return loss. Means at one point only my antenna is working. This antenna is working, right? So we should see a dip. At that particular dip, my antenna is resonating. Means it is radiating. It is giving gain, high gain. So that point is the resonant frequency. Okay.
145 GHz. We can also fabricate PCB designed using Eagle software. Different software tools such as CorelDRAW or AutoCAD can be used to prepare negative of the required design like antenna or circuit layout. The negative is printed on the trace paper. For better accuracy, it can be printed on the transparent sheets. We have printed the antenna negative on the trace paper. We are fabricating the antenna on standard FR4 board. The FR4 sheet is taken and the required size is marked. Now to cut the PCB, we have to use protocircular saw machine. This machine is used for precision high-speed cutting and can be used for all types of boards. Now the file is used to smoothen the edges of PCB. A steel wool is used to clean the board and remove dust.
So he's just cleaning the board, right?
A liquid photoresist is applied on the surface of the PCB for 1 second using rectangular tank which is attached to PCB coater cup and dryer machine. For uniform coating, put the photoresist applied PCB in dryer for 4 minutes.
So 2 times we heat. The first heating is called pre-bake. Bake means heating, and the last heat we do, that is post-bake, right? So this is a pre-bake he is doing.
We can set the 4-minute timer by pressing the start button. Now after the baking, remove the PCB from dryer. The EV unit is used for single or double side exposure using the UV tubes.
So this you can see are the UV tubes. On this he will make the design, right? The image.
A sandwich glass assembly is used to provide excellent tension between the negative and PCB.
So this is the negative. He will just put it and he will leave it, and this image will be pasted on the substrate, right?
Here we are doing the both side exposure, and a timer of 2 minutes is set using the start button.
So just image, and image will not be visible, right? It should be developed, then it should be post baked. You will see this.
After 2 minutes, take out the PCB from exposure unit.
So this is the developer. This liquid has been given negative photoresist, right?
The next step is to develop the image, for which we have to use LPR developer.
So you see nothing is visible here. It will be visible after post bake.
For post baking, put the PCB board in dryer for 2 minutes.
So this he will dry. That is post bake. Post bake means after that developer solution. Now you see the image is visible. Okay.
You can see that.
And all the unwanted things should be etched out, should be cut. So that we will use this etcher. So this is the etching unit. It will etch out the surfaces, unwanted surfaces. Okay.
Board is completely dry. The next step is etching. Hold the PCB using plastic clips. Put the PCB in easy etcher for approximately 4 minutes. The etcher is used to remove the unwanted copper from PCB.
See how it does.
The equipment includes the heater and the airflow compressor.
So you see all this unwanted copper which is not needed here has been etched off. Okay.
Now you can see that
So this is the copper. Here there is no copper. Okay.
all the unwanted copper is removed from the PCB. Now the board is cleaned using water, and we can see the front and back side of the antenna.
Now he will cut this. He will cut this.
The extra substrate is cut using the protoscope.
So this is the substrate, this is the antenna, and this is the connection, feed. Okay. So this is one video. Other is this, how to solder it. That is still there. You can see this.
Hi, hello. So welcome to this tutorial on how to solder USB connector to a patch antenna. So what we see on here is a rectangular patch antenna with transmission and feed.
So he will solder, right? So we'll just see the technique how to do. That's all.
Going to work at 2.45 gigahertz. So as we solder the connectors on, you'll be able to measure.
For each and every antenna, we know there is a frequency of operation. So this antenna is working at 2.45 gigahertz ISM band, right?
Using our so let's do that then. First of all, let's get this. So you can buy the pins and type.
This is the
The stickers, which is our brand name.
thing.
Widely vended. Now the reason I do that is that we have,
So proper soldering, he is making some space, right?
solder the connectors on to
And this is the pin.
of course the other thing that we can do is to get a very
And now soldering will start.
how I find having a thick tip works. Not all PC
But there is some point here in soldering.
use that I do. Okay, so once again, now it's very loose now. Once this
So here it is loose, right?
stick has gone off. So what I tend to do
And here it is. You see, these two pins should not touch the feed. If it touch the feed, these two pins, if they touch the feed, then there will be coupling, then there will be losses, right? So soldering should be very effective, that it should touch only substrate, not the feed. Okay.
do is solder the top first. So make sure the transition line. Now, the other thing is why would there be pins there? There's something called coupling transmission line where there's this side here is also metal, so that will be what you saw. Now, with some sort of pins already has no pins. So that runs on together. You can see some liquid, and that is usually what they do. Okay, you've got to do it quite. I don't affect the 50 or so therefore you've got to be quite choosy. So what I would say is get a piece of water PCB and just try this out first before you do 3. Some solder. Oops. Solder off. There we are. 1, 2. Okay. So now next thing is that's it. So I use something called a piercings tool.
Okay. So yes. So we have seen the soldering and the fabrication. Now, as I said, millimeter wave starts from 30 gigahertz to 300 gigahertz. And applications are many wherever we need some high-speed wireless network, let's say Wi-Fi and WLAN, that is 2.45 gigahertz or 2.4 gigahertz band. Their speed is very less. So when we use to make antenna for very high speed applications, like, so in that case we have to use this millimeter wave technology. So that is for high speed wireless technology. Telecommunication radar means high frequency radar. We will use this millimeter wave applications and the imaging also, right? So this antenna which I have seen, which we have seen earlier, means this antenna corresponding to this. So this antenna, see, the gain is a 4.6 and here it is 6.5 dB directivity, along with the return loss of minus 23 dB, right? And VSWR of 1.12. Using parasitic patches, slots, and all the performance enhancing techniques, we have improved it. And then, so this antenna, which is working at a 30 gigahertz with this much parameter, and it is very much in comfortable zone, right? Because VSWR is VSWR is voltage standing wave ratio, that is Vmax upon Vmin, and it should be close to 1, right? Here it is 1.12, right? Ideally, the value goes from 1 to infinity, right? But it should be very close to 1 or at most 1 to 2, right? Return loss should be less than minus 10 dB. Why? Because if it is minus 10 dB, means 90% of the power will be radiated into space, right? Then my antenna will become an efficient radiator. So that way, and here it is minus 23 dB. So that is the thing here. Okay. Then, so this is the conferences that these are my publications. So from in the last 2.5 years. So that's it. So conferences, and then these are my journals that I have published over the 2.5 years. So this is that's all. And if you have any query, you can raise. And that's all from my side.